Okay, so let's get started. Um, so the topics, the intentions for some of the students maybe have either competed or known of the competition, but the talk would be at the level where people for students and all parents who has not done uh, competitive programming and want to learn about it. So it should be, we don't assume that you already know about, competitive programming or USICO in general. I mean, specifically. The reason why I I give this talk is Dr. Chen has been teaching for many years, and some of her students or the parents of some of the students has asked her many times about USICO, and I start training a group of her students starting last summer, who have learned 2 years or some of them maybe 3 years programming, um, and has and are interested in um, uh, participating in the USICO competition. So I started the USICO training last summer with these 8 students, and they all done very well. So then they're more interested in, more of the parents interested in learning more about what's USICO about, and then how to prepare for it. So that's really what this talk about. So let's start with, can you guys see the PowerPoint? You can all see the PowerPoint?
Yeah.
Okay, good. Yeah, great. So this is all about the reason why USICO has become more popular, or at least more people talk about it, more people heard about it, is because there are more and more people taking computer science classes, right? So, or coding, whether they are learning it from school or they're learning it from after school. There are definitely more students learning it from, obviously, middle high school student, but there are also people, even students in elementary school, learning it. And obviously, the reason for that is people recognizing important computer science. So then, but more specifically, this talk is about what is USICO, right? Or and then how do you prepare for it? And then I hope this more fundamental question is, why? Why do you want to participate in USICO, or in fact, why do you want to learn computer science? So that's really I want to get, at least give my perspective from this. I have a background in computer science from many years ago, and I have, over the years, I've been involved in computer science, and the last several years I've been going back to teaching computer science. So what is USICO? Or USICO stands for USA Computing Olympiad. It actually has a quite long history. It started in 1992. It's not many years after IOI, which is the International Olympic of Informatics, started. So through USICO, they select, the organization select 4 students to represent USA to participate in IOI. But USICO is actually a lot more general than the 4. Obviously, you say, well, how do you become part of 4? It's 4 in the whole country. But it's, in fact, it's really a good way for you to learn and then to be able to level up, in fact. So, in fact, you can recognize your learning and achievement. So it has this very good set of problems, that's to start with. And they're all focused on computational thinking. So if you are not familiar with what computational thinking is, then let me just stop the video. So then you can, through this talk, hopefully you get better understanding. So that's part of the purpose of the talk. And then the next thing is that it's very easy to participate. It's free, it's online. And every year there's 4 times, started in December every year. So the season starts in December and goes on to March. So the last open competition just ended 2 weeks ago. So in March, I think around March 15th. and you can do it online. So you just register and do it online. And there's multiple levels, so you can start very easily at the bronze level, even though challenging. But as you can see through this presentation, you don't really need to be like take 3 or 4 or 5 year computer science to do that. In fact, there's it's more about problem solving skill, right? But then you can obviously, as you get better, you can progress to silver level, gold level, and platinum level. So you can achieve that. And then it also, very importantly, it supports multiple languages. So it does not require you to learn C++ in order to participate. Or you can do C++, Python, Java, even Pascal. So I don't know many of you still learning Pascal. So again, the focus is on testing your computational thinking ability, not like what language you know. In fact, not like how much you know about language. So, and if I just look at some data when I'm preparing for this talk. Obviously, just from the students, we are getting more and more interest in that. So Computation Olympiad is actually, by looking at the number, is definitely gaining momentum. So some people predicted that Computation Olympiad would be like the next math Olympiad, as computer science being recognized, the importance being recognized, as well as the fact that there's in fact more students are learning it, so they all want to find a way to show their learning, as well as also to learn further. So if you look at the last 3 years, so what's interesting though, obviously the U.S. number, the blue number is increasing, but China, and it's a U.S. competition, but you see that many other countries participate, in particular China. So China in December 2019, in that test, has almost half this number of students at US. So it's quite amazing. So the red curve actually represents the Chinese student competing, and that looks at the curve is actually going very, very deep. So actually, how actually should be who should participate, or how you should participate. So it should be who. Sorry, it's typo here. So basically, it's for the bronze level, for students, this is actually from the website. The bronze level student are really for people who just, who have learned computer science, learned programming, but they have not spent a lot of time learning algorithmic programming, right? So they learn the language, they know how to do, the basic programming, the conditional, the loop. If you look at age-wise, I look at, this is on the right-hand side, is I just took a screenshot of some of the people who passed the last bronze level. So they age from the 7th grade to 12th grade. So, wide range. So, as young as 7th grade. And the student I had last year or last season, they're mostly now 9th grade. So they started 8th grade, and there's a 7th grade at the time. And then also there's a 9th grade, now it's 10th grade. So, that it ranges from middle to high school. There may be some very smart kid who started earlier than as early as, I remember seeing a number as early as 6th grade. And the best way to understand what user code is, I believe, is just to look at a problem. So don't be scared, the people say, oh, well, I don't want to look at a problem. So I can tell you this problem, if you know how to count, you know how to do this problem. But I want you, by looking at this specific problem, to give you a sense of what it is the competition is testing, right? So I'm going to just read through this very quickly. We're going to go back to this problem. All the user code problem about farmer John and his cows. So it's all about cows. And so in this particular case, you can take a screenshot, and maybe you can and then you can come back to look at the problem. So basically, farmer John has cows for numbers, but at the beginning, these numbers are not lined up properly. This is not in order, right? So he wanted to order it. But then unfortunately, the cows are sleepy, so he only moved the first cow to some other point, and then so on. But again, we want to come back to visit this problem later, so I don't want to spend too much time. But I want to just tell you, in this talk, we're going to explain what the test's about by analyzing this problem. It's a problem 2 of the Browns level. So normally problem 1 is the easiest, and problem 3 is the hardest. So problem 2 is in the middle, but it's not always the case. So there's a misconception, right? So, and a lot of people think that, some people has asked me or asked Dr. Chan and say, my son or my daughter has learned programming for several years, or 3 years, and they learn C++, Python, and so on. But when they look at a UCICO problem, they don't really understand what it is. They don't even know how to start, and they want to know why. So here's I believe a misconception that a lot of people have. People kind of equate learning how to code to being able to solve problems. So many, and in fact, this is, a lot of coding classes say, or learn to code in 6 weeks, learn to code in, 3 months, but coding are really they're teaching the mechanics of programming. So they usually focus on the language, Python, Java, and some of the more advanced one would, obviously they teach you the syntax, they teach you the data structures, right? What a list is, obviously variables and maybe queues and so on. And then they will teach you algorithms, like what a bubble sort is, even more advanced one, binary search, depth first search and so on, right? But the focus is on the mechanics of the programming. But learning a computer language, right? So they're teaching you you're learning a computer language, does not mean that you know how to use it to solve problems. And I hope this is intuitive to you, right? Because I just give you some example, which is hopefully is you should be feel you're aware of that. So like obviously many people, including little kid, they learn how to use brush, right? And use how to use color, but that doesn't mean that you can be a good painter, right? So a good painter, obviously, you need to learn a lot more, but also a lot depends on your creativity. How do you compose the picture and so on. So learning how to paint, you learn to use a tool, which is important, but then there's a lot more to it. So the key is really in computer science, it's not necessarily just learning the code, but more importantly, how to use coding as a tool to help you solve problems. So that's really what UCICO about. It's really more about how to use the language, whatever language and the coding skill that you gain to solve problems. And it's a creative process. So it's not a mechanical thing. It's a creative process. Just like you build Legos, right? You have all the pieces, but then what structure you end up building, obviously you have to design it, how you want to build it. Same with music composition, right? So obviously you learn how the scale works and so on, but it takes a lot more than learning how to draw the scale, the music note, than to composing music. So computer science is exactly the same. Learning how to code is just the basic, it's a tool. So UCICO is not about testing programming knowledge. So in fact, if you look at, obviously I have, this listed, this is not exhaustive, but for the Browns level is pretty true. You don't really need to know too much about programming, right? So 1 year, maybe 2 years, I think you would learn enough. So you need to know variable, list, arrays, sets, and dictionary hash maps. Maybe you don't learn that in the first year in programming, but you get to it definitely in the second year. Know how to use functions and loops and conditionals and maybe some basic sorting. So you look at it, not a lot of knowledge involved. So it's definitely not testing, your programming knowledge. So, but what is it testing? So how do you? So on the left side is a problem, right? Again, I will go into the detail of this problem in one, in the talk. But how do you, by reading this problem, Farmer John and his cows, that's not in order, and he wants you to help him to figure out what's the minimum numbers of moves to make him in order. How do you read this problem and then end up with a program? This one is in Python that can solve his problem. I kind of give you a hint here with all the things that cover up. The actual solution only has 4 lines. Well, the part in the beginning, this is just reading the files, and this is writing the file. So you need that, right? You read the list in, and then you write the answer. But this problem, it only has 4 lines. That's all you need to solve it. So as you can say, well, it's not a lot of programming. So the question is really, how do you go from a problem to the solution? And what is involved, right? So obviously, just learning how to write code is not enough. So what it takes you to go from the problem to a solution is what we call computational problem solving. But what enable you to do the computational problem solving is what we call computational thinking. So it's really the thinking underlying this problem solving process, where the coding is only at the end. Once you solve the problem, then you obviously need to put in a language, and then make it run, and then provide the answer. So some of you may be familiar with what computational thinking is. Some of you may be the first time to hear it. So computational thinking actually has a very precise definition. It's initially, the idea of computational thinking was initially brought out by a professor at CMU at the time, Janet Wing. She wrote a short paper to articulate that. In fact, she first pointed out that computer science is more than just coding. It's just more than about the language. It's about this underlying thinking that enable you to solve problem like a computer scientist. So, and which has different component, right? So which is formulating a problem is very important, and then expressing the solution, which is the code, in a way that the computer, which can be human, right? You can actually explain, you can write the code, you can instruct the human as well, so that they can carry out, so that they can execute it. So the 4 components of this, I can just briefly describe it here. Problem decomposition. How do you break a problem from big problem into smaller problem, so that you can eventually becoming trivial, so you can solve it, right? So that's called decomposition. Abstraction is, how do you take a problem like the cows and the farmer John, which has a lot of information, how do you reduce it to a simple enough problem in the digital world, so that then you can start solving it. So really the ability to get rid of all the irrelevant information and then represent the relevant information in a way that is concise and is efficient. So that's abstraction. Pattern recognition, which is actually the most important part. For me, that's the most important part. Is how, and even though it's hard to understand, is how do you see similarities? How do you see relationship? How do you start generalizing, right? So in fact, that's when the topic of this workshop is called exploration and discovery. And the process of discovery is you start seeing patterns. You seeing relationship, right? So pattern is more general than just like a flower pattern. It's really seeing relationships, seeing similarities. So that's what we call pattern recognition, very important part. And finally, algorithm. So that's the one where once you see the pattern, you discover something, how do you translate that into a algorithm and then written into your language? So that's the 4 component that makes a computational thinking. So you look at this and say, well, it still looks, it still sounded quite abstract, right? How do you use them in help you to solve problems? So what I would do next is to actually look at a problem-solving process, and then explain how this 4 different computational thinking component fits into that. So if you look at solving a musical problem specifically, but in fact any computer science problem, I really believe that it is just a problem. It is an exercise of defining a digital world and then explore and then discover in this digital world. So it consists of 3 major steps, right? The first step is looking at a problem and analyzing the problem, so that you can come up with a precise description, right? And this is what we call abstraction. So that's why abstraction is so important in this computational thinking. So the outcome of the problem analysis and abstraction is you have a digital description. So basically numbers and as data structures, right? And operation on data. So I just call it digital world. So you come up with a digital world. And then what do you do in the digital world? You explore and try to discover. So you explore in the digital world, just as you would in the physical space, right? So people, when they discover when they discover things in the physical world, you explore, and then you try and discover. So in this process, pattern recognition and problem decomposition becoming critical. In fact, by during the process exploration, you trying to define patterns. So again, I would go into detail of what this means when we go back to the sleepy cow problem. And then through this exploration discovery, what will happen? You can come up with a hypothesis. You say, oh, in fact, this is what governs this digital world. So you say, this is the rules that govern it. And then from there, then what do? You validate. So once you make a hypothesis, you believe this is true, right? Then you need to somehow validate it's true. So this is actually where you develop the algorithm. This is where you actually write the program. And then you validate it, by run the program through numbers. And if successful, well, then you're done. But often you're not successful, then you go back and see if you missed something in discovery. Or you miss some information, you recognize the wrong pattern, you decompose the problem not in the right way. So you look back to that. But it's also possible that the failure is due to your models initially done wrong. So this is if you look at all the computer science problem solving, and more specifically, USICO, which represent very, obviously from simple problem to complex problem, that's the process. That's how you go from what we saw before, the problem, to the code. So now, as I said earlier, I would, maybe this looks familiar, still very abstract or unfamiliar to you. So I would just go through these 3 steps using that cow problem that we saw earlier. So first step, problem analysis. So as I said, this is the process of abstraction, right? So you look at the word here, right? A lot of word, Farmer John. Well, Farmer John is not really important here, right? But the important things are the cows. So let me say I can do the imitation. Well, so they're N cows. So this is important, right? N cows. And the number actually, that sometimes as you get harder and harder problem, this is bigger than 1, less than 100. This number is actually important, but in this case, it's just less than 100 cows. So then the second important thing is that the cows in some order. So initially, it's not in the order of 1, 2, 3, 4, 5, right? So it's in some order. So I just using example here. So the cow, right? So the cow in this case is actually order 4, 3, 2, 1 in the reverse order. Now, what Farmer John wants to do is that he wants to make them into the order from 1 to n, right? So you want to order them. The only problem is that the cows are sleepy, so he can only move the first cow to somewhere. So he cannot just say, oh, let me switch 1 and 2. Cannot. He can only move the cow. Farmer John standing here. So let me draw Farmer John here, right? So Farmer John standing here. He can only order the cow that's next to him. So he can move 4. He can move 4 to anywhere. And then 3 would slide over and then become here. And then you can move 3 again. So that's the problem, right? So you read the problem, you trying to either by paper or in your head, trying to visualize the problem, right? Now, once you've done that, so then, as I said, what we want to do in this step is that you want to somehow abstract take out all the information that's not relevant. In fact, all this thing, so obviously, farmer, the farm, in fact, the cow is not important in this case. Then the goal is you want to construct a digital world, right? So what do I mean by digital world? The digital world normally contains three things. You have data. So again, like I said, the cows and the farmer johns are not important. It's this array of the cow's ID initially. So in this digital world, you have an integer array, 1, 2, 4, 3, right, representing, corresponding this. So this, in fact, it represents a state of the world. Now, in this world, what you need to have operation. What can you do in this world, right? So in our case, very simple. You only have one operation. The only thing you can do in digital world is you move the first element, the 1, to somewhere down to the right, right? And then obviously all the other elements shift, and then the 1 becomes here, right? And that's the only operation. And then you can do it again. You can move the 2 somewhere. So the only one operation. And then what's the question or the task in the world? What are you trying to achieve in this world? Sometimes you want to order the list, sometimes you want to move something, but in this case, there's a question. It's a question of what's the minimum number of time of move that you need to do in order to make the cow in order, 1, 2, 3, 4, right? So that's a question. So this is what I meant by the digital world. So in the first step in the abstraction process, you want to create the digital world. Now, the next step. So what do you do in the digital world? So now you have the array, you have the number, you can move the first element. What you're trying to do in order to come up with a solution or to come to the answer to the solution is that you want to start experiment. You want to start exploring in this world. So what do you mean by exploring? What do you mean by exploring? Hello? By exploring, you can start applying the operation, right? You remember the operation is you can move the first element to the left, to the right. You start applying the operation to the data and then see what happens. So that's what we call operation, exploration. And then through the operation, you want to discover something. And then once you discover something, then you hypothesize. You come up with, say, oh, this is actually what I discovered. So let's go through this cow problem again, and trying to see, and trying to see what what this process means. And I print this thing from a simulator I did. So, but anyway, we'll just do it on the PowerPoint here for now. So here's the order, right? Remember 4, 3, 2, 1. Now, what we can do is when we move the left cow to somewhere, right? So it moved to the right, and then basically the cow will assume the position, and then all the cow that this cow passed or this number passed, right? So you move the 4 to here, and then you pass 3 and 2. 3 and 2 got shuffled to the beginning. So now 3 become the first one. So that is really what do we mean by applying a operator to the data, right? So exploration, that's what you do. You move the cow, and then you you see what happened to the rest. Let me see if I can, yeah. So let me do let me share this simulator and try to do it a little bit. So here's different cow, right? So this is a 4, 2, 3, 1. So how do you move it? We can only move the first cow. So we can only move the first cow. So we move it behind 3. Well, they are 3 and 4. Well, that's not good. Well, so maybe we move 3 behind 2, right? And then you move 4 behind 3. Well, that's not going to do us anything. So let me move this behind 4 and see what happens. And then we move this behind 1. And then we move 3 behind 2. So now we're done, right? So the simulator actually can check. It said I've done 5 moves, but the actual minimum moves is 3. So, well, we must have done some wrong move, right? So now we go back and let's generate another sequence and see 1, 4, 3, 2. So let's think about, so 1, well, so we move 1 because 1 is already smallest, right? Now, but we see 4 is bigger than 3, so we definitely need to move 4, right? But in order, before we move 4, we need to move 1. So where should we move 1 though, right? So, well, let's move 1 here. And then now we can move 4. So where should we move 4? Should we move the 4 here? But if we move the 4 here, there's a problem because 1 is smaller than 4, right? So then if we move the 4 here, well, the 4 will need to move again because well, 1 is less than 4, right? So should we move the 4 here? Well, it's bigger than 1, but this, so it's okay for 1, but then the 2 is still smaller than that, right? So that's not good because if you move it here, the 4 will need to move again. So then the best way is to actually move the 4 here, right? So you have that. Now we can move 3. So where should we move 3?
Behind 2.
Yeah, behind 2. Now, good. So now, we make 3 moves, and in fact, that's the minimum amount of move. So now, I don't know whether you guys have thought of a pattern. Let's try to do, I'll go back to see, so let's run a little bit more. Let's do 5 cows, right? So now, again, so 1, normally 1 and 2 is in order, right? But so normally we don't have to move 1 and 2, but then, 4 is in order. But then the problem is that 4 is more than 3, right? So we need to, we want to move 4 behind 3. But in this particular, so usually USIC code normally describe a kind of what we call strange wall, right? So if we can just swap 3 and 4, that'll be perfect, right? Then you're done. But unfortunately, in this problem, you can only move the first cow. So now if you want to move 4, you need to move the one to the left, right? Before you can move 4. So then we need to move 1, right? So where do you put 1? Well, can we put it here? Well, can we put it here?
Put it behind 4.
Yeah, right behind 4. Okay,
behind
so I'll ask you
4.
ask you why in a second. So put it right behind 4, put it here, right? Now we can move 2. So where do you put 2?
Behind
Between 1 and 3.
Yeah, between 1 and 3, right? And then now 4, where do you put it?
Behind 3.
Yeah, so now put it here. So in fact, we did it. You guys did a good job. So we have 3 move, and then that's the minimum. So take a second to think about. So we did this experiment, and obviously you in doing a USIC, you don't have a simulator. You do it on paper, or in fact, hopefully you can do it in your head. If not, you with the help of paper and pencil. So through this experiment, we just did very quickly. We want to find out there's some underlying relationship or some underlying rule that governs this interesting wall, right? So can we now switch back to? So we want to find out. We want to find out what is really govern this interesting, cow swapping wall, right? So hopefully, the student who just give me the answer, you have figured out. So the first discovery, as we do, and then from your answer, we realize this. We try to figure out when we take the first cow, where should we move it, right? If we move the cow like we did when we make the mistake, if we move the cow to a position like here, that it still has cow that has a smaller number to it, it's not a good idea, right? You wasted this move because we know why. Because then you need to move it again, right? Because it's in the wrong position. 4 is larger than 2. 4 needs to be after the 2, right? So you need to move again. So then basically from this, we come to a conclusion that, or discovery that, when we move the cow, the leftmost cow, we always trying to move it to behind or to the right of all the element that is smaller than it, or put it the other way. You move it to a position such that all the element to the right is bigger than it, right? Otherwise, it's a wasted move. So that's the first discovery. The second discovery say, okay, so then how many cows do I need to move, right? So you look at this one. So obviously we move the 4, right? We move the 4 to after the 2. But then, so it becomes that. But then we're looking at 1. So do we need to move the 1? We have the same problem when we do the simulation. Well, the 1 is already in the right order, right? But unfortunately, 3 is not in the right order, and we need to move 3 to behind 2. Given this strange universe or strange digital world, you can only move the first item of the leftmost cow. So in fact, you need to move 1 in order to allow you to move 3, right? So that's really the trick. So now you need to move 1 so that now 3 is exposed. So you can move 3 to 2, and now you're done, right? So those are 2 discoveries that we have when we're going through the experiment. Now from here, after you go through this and you realize, this is what I need to do. I need to move the element that I need to move is, number 1, I need to move it to. Where do I need to move to? Second, how many elements, right, I need to move. Hopefully you realize that. So here's a hypothesis. So hypothesis is this, right? So really, it's a little long, right? So we recognize that we only need to move we only need to move the last cow that is out of order. The last cow that's out of order. So if you look through here, and then hopefully, you can think about why, right? So look at this list, the new list. So what's the last cow out of order? Is 2, right? So 1 is already in order. So 1 is bigger than 5. Do we need to move 1? No. We only need to, because 1 is is bigger than 5. So this is already in order. All we need to move is this 3 cow. But when we move them, we make sure that they are being inserted in the right order as you move them. So then we come to this hypothesis, which is, as long as we find out what the last cow out of order is, then we know exactly how many moves you need. In fact, the problem does not ask you to actually do the move. They don't ask you, okay, show me how to move it. They only ask you what's the number move. But in fact, when we do the experiment, we actually know how to move, right? So we first move the 4 here, and then we move the 3 here, but up before the 4, and then we move the 2, right? That's how we do it. But the problem only need to ask you what's the minimum number move. And then from the discovery, we come up with this hypothesis, which is, in mathematics, you would say this is a conjecture, or this is a conjecture now, right? So we only need to move the number of cows that's including this one, right? So if this one is cow K, then the number is K moves. So once you come up with this hypothesis, well, you're pretty much done. So obviously the next step is to verify the hypothesis, right? So how do you verify it? You write programs. So hopefully you guys know how to write simple. So the program that the 4 lines are this. So the pointer, this one, is the one that counts which cow is the last cow that out of order. Okay. So we initialize to be -1 because 0, as you all know in Python anyway, 0 points to the first cow, right? So 0 is actually in the array first. So then we go through each pair of cow and compare them to see if cow I is bigger than cow I plus 1. So is the left cow bigger than, if the cow bigger than the one next to it to the right, right? If this is true, then you remember that. You remember that in the pointer. And then you keep going because we want to find the last one. That's our order. So once you go through all this loop, you go through all the n cows, then you find the last one, that's our order, and then you just output, all you have to write answer, pointer plus 1. Why plus 1? Because you remember that in the array 0 is the first one. So in Farmer John, the cow number from 1 to n. So that's it. 4 lines of code. I mean, including this is the beginning to read the file in and write the file. I'm not going to go in detail how to read file and write file, but you guys should all know about. If not, this is standard. You can just learn it very quickly. So if you see, the trick to, or the key part of solving this problem is really discovering this underlying rules, right? Or this underlying patterns. And once you figure that out, the coding part is almost trivial. So once you do that, then what you do, you submit to UCCO, and then they actually, UCCO have cases. So there's 10, 11 cases, right? And you submit them, and they check each case to make sure it's correct, and then you're done. So so let me just summarize again. So quickly summarize what this process about, right? In solving a computational solving this problem. So here's a problem, right? So this is what you're given to you by UCCO. So in the first step is abstraction. So you want to create a digital model of what this paper, or what this called word problem, I guess word problem. You want to create a digital model for it, right? Which consists of data, operation, and a question, or a task, right? So you create this digital world. Then what do? You, through exploration, so that's the main part, right? So we go through the cow simulator to explore. You can obviously do it on paper and pencil and paper, right? And during the exploration, you pay attention to trying to identify patterns and relationships in this digital world, right? So we, through the exploration, right, through just applying this movement, we and the students also have done that. We recognize, oh, there's actually this relationship, right? So this is how I move it. And then you finally realize that, well, I only have to move all the cows one time. That's to the left of the cow that's out of order, including left cow. And based on that, well, coding up is rather straightforward, right? So that's a step. The abstraction, or we call problem formulation, and then the exploration and discovery, right? So that's the solution process, and then finally code it, right? So those are 3 steps. So now I think a lot of students or parents ask me, right? So what are the important skills that, so in this solution process, in the 3 steps, what are the important skills that for what we call algorithmic problem solving or computational problem solving? I come up with 5. I mean, people organize it differently. Some people have more, some people have less. But I believe these are 5, very important skills for a student in order for them to solve problems effectively, right? Solve computer science problem effectively. So the first thing is visual thinking. So when we go through the cow, right? So I use a simulator to help us to do the experiment. And this cow experiment is actually quite straightforward, right? Compared to other problems, it's quite easy. So that's why I use them as an example here. But a lot of problems require you to be able to visualize in space a line, a plane, and 3D, right? So 1D, 2D, 3D, and ND space. So that's one thing, so to be able to visualize in space. The second is you'll be able to visualize in time. What do I mean by visualize in time? You should be able to visualize a process. So for example, you should close your eyes and think about how you move the cows and what happened to the numbers, right? You move the leftmost number to somewhere, and then what happened to this new set of numbers, right? So you should, so the process, or what we call simulation. So you should be able to, in your head, be able to simulate, to visualize that. And finally, you should be able to visualize relationship. So it's not just space and time, but logical relationship. A city is connected to another city for some of the problem that we saw was called routing problem. So how a city are connected, they're connected by different type of travel plan and so on. So relationship. So that's the first thing, visual thinking. A second ability is abstraction at multiple levels. So you say, well, that's hard, right? So it's really, abstraction is about how you would get rid of all the information not relevant, and identify information that's relevant, and more importantly, represent them in a proper way, right? And how do you represent them in a proper way? That's what we call the digital world. How do you do that? And the third is problem formulation. It's really how, part of this abstraction of problem process is really how do you look at this problem? If you look at a problem differently, you would do abstraction differently, right? So, because if you treat the problem this way, and you might end up using certain information that's given by the problem. But if you look at a problem differently, then you would ignore those information. In fact, the trickier type of musical problem are all things that trick you to think the problem you should think this way, but in fact, you should think differently from an opposite way. So in a part of this formulation or thinking from different perspective, I have this thing called reverse thinking. So think from different perspective, and one very a different way to think differently is to think reverse, right? So in fact, in the when we look at the harder musical training in silver level, we spend time on training students how to think reverse, right? Because we normally think one way, and it's difficult to get out of the habit, right? So, but looking at problems from different perspective, thinking reverse, so those becoming more important skill when you progress in a higher level of the musical or more difficult problems. Inductive reasoning. So in fact, if you look at how the whole discovery, explore and discovery, they're formally called inductive reasoning, right? So you are trying to look for patterns. You're trying to generalize from cases, right? We do a few cases, and from there, you trying to come up with a generalization. You say, oh, this is what I believe, right? So that's called hypothesis, or mathematically called conjectures. So this is called inductive reasoning, as opposed to deductive reasoning. So finally, this part is also, you might not heard of the word metacognitive reasoning or metacognition. So metacognition is really, if you put it simply, is think about your own thinking. Now, the reason why this is important is that you need to, because computer science is not about you knowing how to solve the problem, right? It's about you programming, or what we call teaching the computer solve problem. So in order to the final step in developing algorithm, right? So you have this discovery, you say, oh, this is how the cow moves, but then how do you, so now you know how to solve it, right? But how do you take what you know how to do and then convert into an algorithm, which is basically to teach the computer how to do it. So that requires you to be able to think about your own thinking. So think about your own solution process. So what we call metacognitive reasoning. So those are, very high level, those are very important skill for someone to become a good computer science problem solver. So how do you prepare for USICO, right? So, many, we talk about, so hopefully you guys will look at it, well, many of the students who are listening, I think you have the programming background, right? So I think you have taken, 1 year, 2 year programming. I think you would have, to a certain extent, the programming background. Now, so the prerequisite is that you need to know how to code, right? Because that's the tool, right? So you need to know how to do, how to use a tool. So you take, introductory to computer science. I know some of the students are taking Python 1, Python 2 with Dr. Chen. And so those are basic. You need to know how to code and the basic computer science background. So for USICO, it's really training more on the problem solving skill, which is on the abstraction and the abstraction and problem formulation, and also on the discovery, right? So that's really the focus. If you go from being a good programmer to being a good competitive programmer, in the sense of you compete in solving problems, right? So really focusing on developing the 5 skills that I just mentioned in the last slide. One thing that, this is actually a famous quote from Donald Knuth. It's not exactly this quote, but you need to recognize that computer science, not really a science, is an art. So So many people say, oh, how do you come up with a solution? Well, I can't really give you a formula that you follow that and you solve it. So it's not like, so in that case, it's not a science, right? Although there's the science component to it, but coming out with the formulation, coming up with a solution is really more an art form than science. And given that, it's all like all other thing that you do, whether art or sports or dance or whatever else, right? Or even so I know some of you do mathematics competition. It's about practice. I don't think there's any shortcut that I can give you a formula and say, oh, now I can now pass all the UCICO contest. I wish that's so easy. I don't know how many of you actually read this book. If not, I guess if you're already middle school or high school, I recommend you read it, and particularly relevant in this case of this virus. It's called Outlier. So in Outlier, there's very, very interesting cases that he studied, including the black swan type of event. But one thing that Gladwell brought up was this 10,000-hour rule. So if you heard that, great. So he studied Olympic athletes. He's concert pianists or whatever. He recognized one common theme is that they all have practiced more than 10,000 hours before they become at that expert level. So for UCICO, I don't think you need to practice 10,000 hours. So you look at it, I actually talked to some people. At each level, if you solve roughly, I think you need to solve about 100 problems, right, per level. I know the group of students I trained last season, together, at least together in the class, we did about 100 to 150 problems, about 3 problems per week. So we did 3 sessions, yeah, 100, at least more than 100 problems. So I think it's just practice. So before, so one thing though, so that's it, that's about UCICO, right? So now, I want to bring up 2 points that hopefully is relevant to the student and maybe to the parent who are listening. Why do you learn why do you learn computer science, right? So some people say, well, that's important, but then why is it important? So more importantly, how does computer science differ from other subjects that you learn? Knowing that, or how does computer science, what does computer science bring, right? That is not, that's not by the other subject matter, right? Because knowing that would, number one, would help you focus on, studying, like, right? Second, they will tell you why should you learn computer science? Why should you participate in UCICO? So there's 2 things that we kind of, that's really the cover of the talk. Computer science, the main thing is learn to discover. And I can, I'll go into that a little bit and explain to you how the other classes seldom give you the opportunity to do that. And then the second is learn to teach. Also, it's not what you normally do in other classes. So learn to discover. So, whether physics or math you learn in school, particularly physics or chemistry, you're normally giving, you normally learn the knowledge. The knowledge, they just give it to you in the form of formula, right? And then you solve problems, right? So, I don't know how many of you has learned physics, right? So, F equal to ma, well, there's lots of interesting problem you can solve. So the focus on deductive reasoning, right? So this is more, technical. So you start with, a theorem, right? They're given to you, and you try to derive a conclusion. So you do it deductively. But there's seldom, you're not giving the chance of figure out, well, where does FMAE come from? How did Newton come up with that, right? What's the thought process? What he experienced that led to that, right? So where does the hypothesis coming from? So computational thinking is about that. Where is the hypothesis came from? How do you come up with a hypothesis, right? So we came up with a hypothesis with the cow. So obviously very simple universe and very simple hypothesis. But that's really what computation about, is really allowing a student to explore and then discover, right? So this is something that, this ability, traditional classes does not provide you a good way to do that. Second is learn to teach. So, and traditionally, so let's look at a very simple thing, right? Sorting a list. I want you to sort 5, 4, 1, 3, 2. Well, most kids, even at first grade, I guess you can sort it for me, right? Move the 5 and so on. So you normally do know how to do it. So that's it. If normal problem, math and physics, they give you a problem, you solve it. But for computer science, that's not it, right? You must write code, right? So you need to teach. So writing code meaning that you need to teach what you know to the computer so the computer can solve it. So it's a 3-step process, right? So I'm giving a task, I think about it, so my cognitive reasoning, then I teach the computer, write instruction, what I call instruction space, and then the instructions solve the problem. So that's why it's computer science hard for a lot of people. It's not you're solving a problem yourself. But in school, most of the subject you learn, you are learning how to solve the problem yourself. You are never required to teach, right? So to take this one more step, I just want to bring this up. So a lot of focus on learn to code. In fact, you look at a lot of advertisement, a lot of classes, you say learn to code. But there's a new saying, is code to learn, right? So many schools are focusing on learn to code. But coding, as we, this go back to my very first slide, it is just this tool. So it's really how does a student use this tool to help them better learn. I think that's really what we're striving at in teaching student computational thinking. We're teaching them, programming, we teach them how to think, but really we want to teach them how to use the tool for them to learn better. That's what the goal is. So if you look at UCCO problem, so obviously for many students maybe, they want to pass a level, they get recognition, that's great. But UCCO in fact is at least one of the ideal platform for student to give the student opportunity to use coding as a tool to learn to how to explore and how to discover, right? So I believe, this is what we are trying to do when we're trying to train students to go to do UCCO. Obviously, we want them to pass a level, we want them to get promoted to the next level so that they can be challenged more difficult problem. But the whole process, the underlying reason is that we want them to learn how to use computer coding as a tool to allow them to develop this new ability, right? The cognitive and metacognitive skill that we mentioned. So in fact, this is the real meaning for learning, what I believe for learning to compete in UCCO. So I would, we almost run out of time. So I'm going to leave you homeworks, right? So for the students, take a screenshot, or you can actually look them up on the UCCO website. So both these two problems are from this year's UCCO, just passed, this season, right? So it's last December, and then January, and then there's one in February. Yeah, February. So, so the first problem, it does not, hopefully you read it, you can solve it if you know how to, the basic programming. The coding, more than 4 lines, but hopefully the problem is much easier to formalize or to formulate. The second problem, the math scientists, are slightly more difficult to, again, I want you to look at this problem and put that, the abstraction, how do you formulate a problem, and then how do you do experiment, do on paper and pencil, and then how do you come up with, see if you can identify some patterns, and then you can hopefully come up with a hypothesis, and then you can code it. I coded both, so and then you can, in fact, you can register and submit it to UCCO, right, to check it. Again, so this is the second problem. This problem actually a few more lines. This problem, obviously more than 4 lines, but I think it's like, maybe, the part of the solution is like 8 or 10 lines. So here's also a way for you to, obviously you may not be able to solve it right away, but I want you to get a sense what the problem is. If you can solve the first problem, or at least you can come up with not coding it, but you can come up with a what do you call a flow chart or something to solve this problem, like a pseudocode, then I think, you would have the reasoning ability to go, to get trained for UCCO. Obviously, then, you need to have the fluency on the coding part. If you can do both, then I think you're definitely ready. So take a screenshot if you're interested in trying it. And then, so, I got to mention, I started training a group of students last summer, so they already finished the season. I continue to train them for the silver. So and definitely for the summer, and I'm also thinking maybe starting in the spring, which is a few weeks from now, a couple weeks from now, to start a new season, because it's the first test of the next season is started December. So you never programmed, you never compete before. I think 9 months, 6 to 9 months. So last group of students started summer, so it's about 6 months, right? So we did a couple very intensive classes during the summer, and then we did in the fall. So if this is kind of what we organized the training into 4 sessions. They're building on top of each other. So it's really focusing on what we discover, and then the later 2 sessions is going beyond that. So we know some of the problem 3 has some issue about efficiency, so we start looking at that. And then final one is really just training enough, just do enough exercise so that the student can get the accuracy and the speed, because musical is a time test. So that's it. So let me know you guys have any questions. So I'm going to either you or the parents have any questions. Hello? No? Well, you guys are all on the musical group. So you have additional question after this class, this workshop, just post it to the musical training info group. I'm more than happy to answer. And thank you.
Thank you.
Thank
Yep.
you.
Thank you.
Bye bye.
Thanks.
You're welcome.